Good morning. I'm going to derive the Planck radiation law in full. So, pay attention. I've tried to do it as quickly as possible. To do it right, I'd probably have to spend an hour and a half at it. So it's going to be zappy. Therefore, my general preliminary discussion is going to be kept to a minimum. Okay, so I've had about 4 or 5 lectures already leading up to this. So therefore you should know what spectral radiance is, what intensity is, what energy density is. These things are covered and it takes a long time to go through them. And so here are some more preliminaries. To get Planck's radiation law, we need 2 things. We need the average energy and we need the density of states. Now I'm not going to really go into the details of what density of states is, but you'll see a little bit about it. That's a big topic. I may prepare a whole class on that. It's very tricky and it's very inadequately done in most texts. So, first of all, some preliminaries. The total energy in a system is the number of particles, let's say, times the average energy per particle. If each particle has 1 joule of energy and there's 100 particles, then we have 100 joules of energy in the system. Now, the energy might not be contained in a particle. It could be contained in a mode. That means a standing wave, a vibration. A standing wave carries energy in it. That's what we're having here because we will have standing waves in a minute, not particles, okay? But it could be particles as well. So the total energy is the number of modes then times the average energy per mode. We need this expression. Now, the problem is that the energy is extended over a number of frequencies. It's a spectrum. So we have a spectrum in terms of frequency, lambda or angular frequency, or even energy itself. So to get the total energy, you have to integrate over all those different frequencies. d nu, right? So we'll take the number, d nu by d nu, integrated over d nu, times the energy. That's like a generalization of this. In other words, n is a function of the frequency. E is a function of the frequency. It's spectral. So therefore, when you hear the expression radiance, then you go to spectral radiance, it means you're talking about a spectrum, frequencies, wavelengths, or energy density, spectral energy density, and so on and so forth. We're going to define this object here, the derivative of n and nu. So we need to find an n, a number, how many modes there are in what? In what's going to be our cavity radiator. And of course, the total energy over the volume is going to be the little u, the energy density. An example, suppose n, we find that the number of modes in our system is a times nu to the 4th. This g nu we're going to define, right? G nu is the derivative of n with respect to nu. In this case here, it's just 4a nu cubed. It's going to be simple functions. We'll also define a density like that one too. This is the density of states, actually, strictly speaking. Okay, so that's where we're going. First of all, we need to find the n. What is this n going to be? We need an expression for that. And to do that, we'll take our cavity radiator and we'll make it into a box of sides of length L. So what we're going to do is we're going to set up standing waves. We're finding n. That is an expression for the number of modes in the system. Well, if the box has sides L in the x, y, z direction, then the volume of the box is L cubed. Now we can set up standing waves in that system. And you know the way standing waves work. We've looked at standing waves before when we considered an electron in a box, and we wrote down a solution. The only difference between this and the solution that we wrote down for the electrons is that this is going to be time dependent. Okay, because we're going to talk about these standing waves obeying a wave equation. So in the box, some psi of x, y, z, and time dependence. Now, I'm not going to keep writing in these things all the time. You know that they're dependent on x, y, z, and dt. And this psi is just a function describing the standing wave behavior. It's a solution to the particle in a box. Well, we know what it is. We must have the boundary conditions 0 on the endpoints. At 0 and L, we have the function is 0. So we have the solution, which is standard, and we've done this before. First of all, I put in the time dependence. And the solution, satisfying the boundary conditions in the x direction, is n pi x over L, standard result that I've done lots of times before. So far so good, only used up 10 minutes, I'm doing fine. So now we take the derivative with respect to x. X pulls out. Okay, first derivative is going to be nx times pi over L times cosine x. First derivative. Take another derivative, d squared by dx squared. Second derivative is going to generate cosine, it's going to give it a minus sign. You can try this at home, I'm moving ahead. You can take the derivatives yourselves. We're going to have a squared times the whole function. And the same is true in the y and the z direction. Now, that's equal to 1 over c squared. Second derivative with respect to time is going to give me omega, what is it going to give me? Omega squared t. Times the whole function. And if you want to do this the long way around, you'll just go out and try separation of variables, because really that's all we did to find this solution. That's just done by separation of variables. But this is the situation, and that's going to be a minus sign there. So with the minus sign there, I'll get rid of all the minus signs and I'll take out a common factor. And I'll cancel off the side, okay? So that's the result that we've got. So now we can rewrite this. Now hold on a sec. I'm going to bring over this factor here. So I get this factor here. But really, this is the equation of a sphere, right? And it counts all the numbers of modes in the x direction, in the y direction, and in the z direction. So if I had 100 modes in the x direction, 100 modes in the y direction, and 100 modes in the z direction, I would have 300 modes. So this is going to be our n. N squared, yes? Well, it's not quite, because it's in the volume of a sphere, and we only need the positive values for n. So we'll take the positive quadrant. Sorry, obtuse. It's a sphere of radius n. We'll take 1/8 of a sphere. So the volume of this sphere then Now, 4 gives me 2, 2 3s is 6. And r cubed is this object cubed. So r is L omega over pi c. Now, of course, I'm going to need space, so I'm going to get rid of what I don't need on the board. Now, let me just check my notes here. Okay, I don't think I've made a mistake. I don't need this here now either. So what am I doing now? Yes, I've got this object here, and I'm going to substitute in for omega. Well, omega is 2 pi nu, so it's going to give me 8 pi cubed nu cubed. So therefore our expression down here is going to be pi over 6 times L cubed, which is the volume. The volume of that little box. Now we're going to get omega cubed, which is 2 pi nu cubed. So it's going to be 8 pi cubed nu cubed over pi cubed c cubed. Now, pi's cancel. There's 1 pi left. What have I got? Pi times nu cubed times volume over 6c cubed. Now that's our n. Now we go so our n is this quantity here, pi nu cubed over 6c cubed. Now, is there a factor of 2 missing here? We get 2 into that goes 3 times, 2 into that goes 4 times. So I got that wrong. Four over 3. Sorry. Now I have to multiply by a factor of 2 to take into account 2 polarizations. So there's a factor of 2 here. So I'll take a derivative of this thing here. Now the 3 cancels. So that our energy density, this thing here, is going to be given by that. Okay, so I may have made a mistake here. One way or another, that's going to be our energy density. It's going to be used in the Planck formula and also the Rayleigh-Jeans. Let's look at Rayleigh-Jeans first. Actually, I'm just going to define this one here, the G by L nu. I put it up here. So now, the partition function. First we'll do Rayleigh-Jeans. Now this is the classical continuous case, the Rayleigh-Jeans law will come out of this, but we need the partition function. Now you have to go to your statistical mechanics to find out about the partition function. Partition function is really the basis of all of statistical mechanics. Now in the classical case, it's continuous, Q. That's the partition function in the classical case. So therefore then the average energy per mode for any particular situation is always going to be given by this, as usual. Now we know straight away. When we take a derivative of a log function, it's 1 over du by d beta for the log of, if we have a function log of u and beta. And what is beta? Beta is the thermodynamic temperature, which is 1 over kT. So for this case here, the average is the same as the negative of the whole partition function. In other words, this is actually a Q. Which is all I'm doing here. Okay, so that's our Q. Now let's do this integral. Well, that is the integral there. Negative. Okay, from 0 to 1. So e to the minus beta e. Sorry. Well, this is going to be 0, and this is going to be 1. So far, so good. All right, so I might not have time to do the Planck one in this particular, but I'll try. So while I take a negative of the log, okay. Now that's a positive sign there, I'm sorry. Negative times negative is positive. Well, when we take a negative of the log, it's the same as making it positive. Well, d by d beta of log beta is 1 over beta, and 1 over beta is 1 over kt, which is kt. Now we already found what the g by d nu is, so now we write down our result. The g by d nu I'll get rid of this. Now this is the average energy classically. So we put in for the average energy classically, and then the g by d nu. There it is up there. Now some people write this differentially, just taking the derivative, the differential part, but this is the result, is the Rayleigh-Jeans Law. Now the thing about this one is, this one generates the ultraviolet catastrophe that we previously discussed. In other words, as the frequency gets bigger, so does the energy. Now we have actually run out of time, so I'm going to do Planck. The second Planck works out the same way. Let's see. I wonder would I be able to do it? Would I have time? I'll try. We'll do Planck. We keep that there because that's also true for Planck. Now for the Planck case, this is what happens. The energy is no longer continuous. Planck assumed that the wall of the box, the cavity, consists of a very large or an infinite number of harmonic oscillators. And each harmonic oscillator has an energy given by any discrete number of h nus. 1, 2, 3, 4. So we call these En. Alright? So there are discrete energy levels. Now strictly speaking, nowadays we know that En is n plus a half h cross omega or h nu. But I'm ignoring this half. We're eliminating this half because in Planck's day he wasn't aware of the existence of that half, right? But we still get our result. So let's see. Therefore then, the integral that we had before from 0 to infinity becomes the sum from n equals 0 to n equals infinity of a similar sort of expression. The exponential, this is the partition function in this case now. All right, so I may not have the time to do the full derivation, so I'll do another couple of minutes of this. Now we find the average energy in the same way as we did before. We put En in here. And the En, of course, is given by this one. Right? So En is going to be NH nu. And we have the same thing down here. And very conveniently, it's actually the same thing. I've run out of time. I will work out this expression in the next class. It works out to be exactly the same thing. We will get E equal to be that. And we have dg by dnu. So we can write down the expression for Planck's law using that result. But I've run out of time, and I'm going to post this and just wrap it up in the next class, because I want to show you how to do this summation.